Well, thank you very much. Well, it's great to be here always. And I appreciate this opportunity today to introduce our university and research. So our university, Nara Institute of Science and Technology, NAIST for short, is a national postgraduate university specializing in cutting-edge research and graduate education in science and technology. NAIST is located in Keihana Science City, which encompasses the prefectural borders of Kyoto, Osaka, and Nara. So we currently have approximately 200 faculty members and a little over 1,200 students, so much smaller than ETH Zurich. All of them are graduate students because we are postgraduate university, and about a quarter of them are international from 50 different countries and regions. And NAIST is part of the global academic network with cooperation agreements with 93 institutions in 23 different countries and regions. And lastly, among the 85 national universities in Japan, NAIST is one of only 2 universities that received the highest rating for both research and education in the latest governmental evaluation. As a postgraduate institution in science and technology, our faculty pursues high-level research, which provides our students with an excellent opportunity for graduate training. A renowned example of such impactful research at NAIST is the development of the induced pluripotent stem cell technology by Professor Shinya Yamanaka, who received the Nobel Prize in 2012. And another characteristic of NAIST is its organization to promote interdisciplinary research and education. And initially, NAIST consisted of 3 graduate schools in information science, biological science, and material science. And in 2018, those 3 graduate schools were integrated into one to create an environment where different knowledge and technologies intersect across the boundaries of fields and disciplines. So today, I'm going to showcase just 3 research projects at NAIST because of the time limitation. And these projects represent different approaches to address today's energy issues and reduce greenhouse gas emissions. So the first one is by Professor Kosuke Hara of the thin film semiconductor devices lab. And according to a calculation, if all the cars and trucks on the road were equipped with solar cells and a battery and run without external power charging, it would reduce 15% of the total global CO2 emissions. That would be a huge impact. But vehicle-integrated solar cells must be lightweight, flexible, highly efficient, and heat-resistant. And today's common silicon solar cells are thick and heavy, and emerging perovskite solar cells are flexible and highly efficient, but they wouldn't survive the summer heat on a car's body. And 3-5 compound solar cells used for artificial satellites, they can satisfy all those conditions, but they are too expensive. So Professor Hara believes barium silicide is a solution. And this compound was first identified for solar cell application by Professor Suemasu of Tsukuba University, and Professor Hara at NAIST is currently exploring its potential for vehicle integration. And this barium silicide has a high light absorption ability, and it films as thin as 2 micrometers, can absorb enough light. And this means that lightweight, flexible devices can be fabricated. In addition, the optical absorption wavelengths range of barium silicide matches the solar spectrum, yielding a high theoretical solar power conversion efficiency of 32%. Moreover, it is stable at high temperatures. So the barium silicide semiconductor has the potential to realize lightweight, flexible, high efficiency, and heat-resistant solar cells suitable for vehicle integration. And here is a roadmap to practical solar cell cars. And Professor Har's group conducted virtual screens and identified optimal materials for the other layers of the barium silicide solar cells, finishing the design of the device structure. And currently, they are in the final stage of developing thin film synthesis techniques toward the fabrication of solar cells appropriate for vehicle integration. Okay, now let me walk you to the next project. As everyone knows, AI is changing the world by transforming the way we do everything. On the other hand, AI consumes a large amount of electricity. Indeed, the rapid increase in our use of AI has a concerning impact on the global energy outlook. So there are multiple predictions about how much our increasing use of AI will affect global energy consumptions. And here's one of those by JST, Japan. So in 2018, the total global electricity consumption was 23,000 terawatt hours, including 15 terawatt hours used for AI. And increasing use of AI in 2030 would consume 1,200 terawatt hours. And by 2050, we would spend 221,000 terawatt hours just for AI, which is more than 10 times the total global electricity consumption in 2018. And obviously, this is not going to be sustainable. So Professor Nakashima at NAIST is trying to address this issue by constructing a novel, more efficient processor architecture. So most of the power consumed in today's processors stems from inefficient data movement in the traditional von Neumann architecture, which has been seeing little change over the past 30 years. So to address this issue, Professor Nakashima, a former Fujitsu supercomputer chip architect, developed Lenzo 4, a new data flow-oriented architecture based on coarse-grained linear array, CGLA. So CGLA overcomes the limitations of conventional data flow architectures, offering a more efficient and scalable solution. And according to published data, the CGLA-based architecture can offer energy efficiency 3 to 9 times higher than that of the high-end NVIDIA GPU. And Nakashima has founded a new startup company called Lenzo, teaming up with engineers who were formerly involved in developing the CPUs and GPUs for the Sony PlayStation. And here's the company's initial product line, an AI server and a crypto miner for mining Bitcoin and other cryptocurrencies. And lastly, I would like to introduce plant research by NAIST Professor Taku Demura on a little greener slides. And he's a tree scientist who pursues biomass energy. And biomass, as you know, is a renewable energy source derived from organic materials such as wood and other agricultural waste. And Professor Demura is focused on poplar trees, which are planted and cultivated throughout the world. And Professor Demura's group previously discovered the 7 master genes, VND1 to VND7, that govern wood biomass production. And the Demura lab has successfully established genetically modified poplar trees in the laboratory. And because of their modified VND genes, cells in the GM poplar trees have much thicker cell walls, as shown in the micrographs at the bottom of the slide, indicating that the GM poplar trees have higher density biomass than wild-type poplar. And these GM poplar trees are currently under field trials in collaboration with Tsukuba University, Japan, and Nanjing Forestry University, China. Professor Demura's poplar tree research has recently taken a new development into another direction. He collaborates with Professor Takeharu Nagai, Osaka University, who established bioluminescence system using genes from light-emitting mushrooms. They have successfully introduced such a system into various plants, including poplar trees. So the photos in the middle show light-emitting poplar trees in the light and also in the dark. And this technology advancement has been exhibited also at the Osaka Kansai Expo. So their dream is to develop light-emitting poplar trees for street lighting, which will contribute to the global solution for our energy and environmental challenges. Someday, the Midosuji Street might be illuminated by light-emitting poplar trees like in this image. So that's all from NAIST. I look forward to another opportunity to introduce more exciting research from our university. Thank you very much indeed.